So we're going to start chapter 11, the final chapter in this course, titled Power Series. So what are power series? So let's look at something that we already know. So let's look at geometric series first. And that'll give us an idea how this is a natural extension of that geometric series. So that was summation a r raised to the power k, which means k starts from 0. So that gives us a plus a raised to the power r plus a raised to the power r squared plus and so on forever. Now, instead of using r, now remember r was just a number, was a constant. So first thing is, instead of r, so we are going to use a variable x. Second thing is that here we had this constant a, which was same for all the terms. So instead of a, now we are going to use ck. That means it's another constant, but it can be different for different terms. So every term can have a different coefficient in front of it. So if we do that, what do we get? Summation k going from 0 to infinity. Now instead of a, we are going to have ck. So that means c's, the constants would be different, and instead of r, we are going to have x raised to the power k. So this is going to give us c0 plus c1x plus c2x squared and so on. So this is called the power series. It's a natural extension of a geometric series. So let's see. So what is a power series? Power series is an infinite series of the following form. So exactly as I explained, it is a series that looks like this. Now notice if you stop at n and any particular n, then what you get is a polynomial. But if we continue forever, then it becomes a series. Now let's go to a more general form, just a small change, and that is instead of x, we are going to use x minus a. So x will be replaced by x minus a, where a is a constant. This a has a very important role to play. So, but let's look at it. Suppose x is replaced by x minus a. So then you get the same series, same looking series as before, but every place where you had x, now you have x minus a, and so on. And the same story holds if you stop here, you have a polynomial, but if you continue, then it becomes a series. Okay, so what is this a? The center of the series is a. The coefficients ck are constants. Then this type of series is called a power series because it consists of powers of x or of x minus a. So these are what are called power series. They look strange when you look at it for the first time, but its importance and its role would be clear as we go through this chapter. But before we go to the power series, we have to understand what's the idea of approximating a function by a polynomial. Again, it may seem, why is this important at this time? But you will see why it extends to power series. So if we are given a function f of x, so we have a function f of x, and and we want to approximate it, then one of the best ways is by what is called a Taylor polynomial. So here's the idea. So we are given a function f of x whose first n derivatives exist at x equals a. So this a is our choice. So we can choose. There is a reason for choosing it, which will be clear again later. But a is just a number. If you like, you can think of it as 1 or 2, whatever number you like. Now we want to find an nth degree polynomial that approximates f near a. Please notice that we are trying to approximate it near a. So if a is 2, our approximation would be good and valid near 2. You would not want to use this approximation somewhere near 100 or 500 or some other number. So what's the idea? So suppose this is our function log x. Now we want to approximate it with an nth degree polynomial. So first thing we can do is we can say, okay, let me take n as 1. So what is a first degree polynomial? That means basically a straight line. This is linear polynomial. So that would be a straight line. Okay, so here you see in the red, this is a straight line and our a is 1 in this particular case. So our a is 1. So we are interested near 1, and here is this line which is approximating f of x. But then if you move away from 1, at 1 it's a perfect match. But if we move away from 1, so suppose if you're here, then the error is quite a bit, because the black line is the log and the red one is the linear straight line. So you think that maybe I can improve it by curving our approximation. So you say, okay, let's take n equals 2. Now that would give us a second order polynomial or degree. So second degree polynomial, which means a parabola. So you would try to fit a parabola, which is the blue line here. So this is a parabola. So this is definitely better. You can clearly see that approximating at this place, the error is smaller. So then you would say, okay, how about n equals 3, n equals 4? So you can keep increasing the order of the polynomial. So now let's derive this polynomial that would do a good job of this. So we have a function f, and we have decided on the value of a around which we are interested in approximating the value of f. So a we have to decide before on. Now we have to decide on the form of the polynomial. How do you want this polynomial to look like? So a very general form would be something like this. So my polynomial, this stands for nth degree, which is obviously going to be a function of x, is c0 plus c1 times x minus a plus c2 times x minus a squared, and so on till n. So this is nth degree polynomial. Now if we had stopped at 2, it would have been second degree. If I had stopped here, this would have been a second degree polynomial. Okay, so now what do we need? We need to find the values of c0, c1, c2, c3, etc. So these, if I know these values, then we have the polynomial that we are looking for. Now if the polynomial has to approximate the function near a, then these matching conditions must be met. Okay, so let's see what these conditions are saying. So suppose this is our function and this is my a. So if I were to draw a straight line, that means I want to approximate it with a straight line, then at least one thing must be that the value of the polynomial at this a should match up with that of the function. So you won't take a line like this. That won't make any sense. Okay. So you would take a line that goes through this, but would you choose a line like this? Again, it doesn't make sense. Why would this be any better? So the minimum that you would like is at least it should be tangential. So we want this polynomial, which is a straight line, to match up with the slope of the function. So let's see. You would want the value of the polynomial and the value of the function to be same. Then next you would like the slope of the polynomial and the slope of the function to match so that they are tangential to each other. But then you want to improve it, so you say, okay, how about if we give this line a little curve? So you say, okay, how about if I want a parabola, a second order? So this was P1, now this is P2. So you would want the curvature of the polynomial to match up with the second order derivative of the function. So that is what this is saying. And as you increase the order of the degree of the polynomial, you would match higher and higher derivatives. So we are going to be using these conditions. Okay, so what have we agreed to? P n of a should be equal, if I put x as a in this, what do I get? C0, because when x is a, the remaining terms are all 0. Now we agreed that this must be equal to f of a from here. So this implies that C0 is equal to f of a. So let's keep that in mind. So that was my first condition. Let's go to the second one. So this is my second. So what's the derivative of this polynomial? So let's take the derivative. Derivative of C0 is 0. Derivative of the second term would be just C1. Then this term, this third term, will give me C2. Then 2 will come in front. So 2 times C2 times x minus a. Plus the third term will give me 3c3 x minus a squared, plus and so on. So when I put a for x, then these terms all become 0 and I'm left with c1. Now we had agreed that this has to be equal to f prime of a from here, from right here. So therefore, so I know my c1 is going to be f prime of a. So let's remember this. Okay, let's keep going. So now I'm going to find the second derivative of my polynomial. So the second derivative means I have to take the derivative of this p prime of x. So c1 gives me 0, then 2c2, so I get 2c2, x minus a doesn't give me anything, and the next term will give me 2 times 3 times c3 x minus a. And if I had written down more terms, then I would have gotten 4 times, 3 times c4 x minus a squared, and so on and so on. Now let's put x as a again. So p double prime at a, so if you put in a, you're going to be left only with 2 times c2. The rest will all these will all become 0. Okay, this is supposed to be equal to second derivative of the function at a. So what does this imply? c2 is equal to f double prime of a divided by 2. Let's go once more. So now I'm going to take the third derivative of p. If I do that, this is going to be giving me 0. Here I'll get 2 times, 3 times c3 plus 4 times, 3 times, 2 times c4 times x minus a. This came from here, plus, and so on forever. Now at a, I'm only left with this. So this is what? Let me write it like this. 3 times 2 times c3. This is 0 and all the terms after that are 0. So this is supposed to be equal to the third derivative of f at a. So again, simple to find c3 from here. So what is c3? F third derivative at a divided by 3 times 2. So clearly we have a pattern here. I hope some of you are catching on to the pattern. So let's see. Can we write what Cn would be? Well, when it is C2, it's a second derivative at a divided by 2. When it's C3, it's the third derivative and divided by 3 times 2. Now notice 3 times 2 is 3 factorial. 2 is 2 factorial. So therefore Cn would be nth derivative of f at a divided by n factorial. Very nice pattern. So this thing is nicely written in this box. So let's read this. The first part of it is repetitive, but let's read it slowly. So what are Taylor polynomials? Let f be a function with first, second, third till the nth derivatives defined at a. Then the nth order Taylor polynomial for f with its center at a, denoted by Pn, has the property that it matches f in value, slope, and all the derivatives up to the nth derivative at a. So it's repeating what I explained earlier. The value, this is the value same, slope is same, and so on and so on. The nth order Taylor polynomial centered at a then turns out to be the following. Notice that this is C0, this is C1. We just saw that above here, right here. This is C2, and so on. And finally, we write it in a very compact manner as follows. So now you have to be comfortable with it, and you have to remember this. It's not that difficult. So let me repeat. A polynomial, Taylor polynomial of order n is f of a plus the first derivative at a times x minus a, second derivative divided by 2 factorial times x minus a squared, and so on till the nth. So we have to decide on n and find the Taylor's polynomial. Now, if A is 0, if the center is 0, then a Taylor polynomial is also called Maclaurin's polynomial. So there was another mathematician who had found similar result, but for A equals 0.